Hello everyone, welcome back to the series on artificial intelligence. In this video, we are starting a new topic which is uninformed search strategies, also called as blind search. So, what exactly is uninformed search? Just imagine that you are dropped into a maze with no maps, no hints, nothing. You only know two things: how to move from where you are to the next spot, and how to recognize the exit once you see it. So that's exactly what an uninformed search algorithm does. So it has zero knowledge or extra knowledge about which direction is better. No sense of distance to the goal, no intuition. So all it knows is that is what explicitly given in the problem, like how to generate successor states and how to test whether a state is a goal or not. Here, key points, we can see that because of this, uninformed search algorithms expand nodes blindly following a fixed rule. This could be based on the depth or based on depth, breadth, cost. Okay. And here is the important part. The only thing that differs between the various uninformed search strategies is the order in which they expand nodes. So that's it. Same blindness, different expansion order. There are six major uninformed search strategies we will cover across this series. So, which are like breadth first search, uniform cost search, depth first search, depth limited search, iterative depending search, and the bidirectional search. Today we will focus on one breadth, breadth first search, or you can also call it as BFS strategy. Breadth first search explores all nodes at a given depth before moving to the next depth level. So think of it as like ripples spreading out in the pond. So first the innermost ring, then the next ring, then the next, always moving outward evenly. BFS is let's take a highlighter like our pen as so we when what about ripples, if you see that, if let's say this is a pond and you see someone is throwing a stone, then you see that ripples starting like this, then they move, then see, then the outer part you can see, then the next string. So likewise you can see that it is moving outward evenly. BFS is implemented using a first in, first out model. So that means whichever node entered into the queue first gets expanded first. All the children of the root, says if let's say this is the root, and all the children of the root node are expanded first, then their children, right? And so on, level by level. Let's see this example that we are seeing on the screen. Let's walk through this. We start at a node. We start at a node. Let's take a different highlighter. So let's say that we are starting at a node A. That's our root. Our A generates two children, which are B and C. Then go into the frontier, our Q. Since it is a first in, first out, we No, we now expand B first. Okay, first in, first out, as you see here. So we are expanding the first one, the first in, and we are taking it as first out. So we now expand B, which generates new nodes, which are B and D. Who are the children of B? Which are D and E. So now let's say that D and E added to the end of the queue after C. Now we expand C. So now we expand C. Next we expand, if you see, because now we expanded C, who are the children of C, F and G. So notice the pattern, the frontier keeps growing level by level. First BC, then we can see that CDE, then DEFG. See, always processing the older nodes before newer ones comes. New nodes are inserted at the end of the frontier. Now, for the properties, if we see, so here BFS, is BFS complete? Yes, if the solution exists. Okay, then you can also say that so we can also we can guarantee that BFS is able to find it because it systematically covers every node level by level. But is it optimal? Yes, but only when every step costs the same. If all edges have equal cost, the first solution BFS finds will also be the shortest one. But BFS have some serious drawbacks, which are time complexity, as you see here, the disadvantage, the time complexity and the space complexity. Here if you see it is a power of the B power D, where B is the branching factor and D is the depth of the solution. So as if you see the P power D, that means it is growing exponentially. For example, if each node has just 10 children and the solution is 10 levels deep, BFS may need to store around 10 billion nodes in memory. That's the price you pay for BFS guarantee of finding a shortest path. That means it needs enormous memory. So to summarize, BFS is complete, optimal for uniform cost, but memory hungry. So that's about BFS. In the next video, we will look at uniform cost search, which is essentially BFS smarter version or smarter cousin, you can say, built to handle situations where costs aren't all equal. See you there.